Okay, take two. If you're watching this on Twitch, welcome. If you are watching this on YouTube, consider yourself fortunate because I just talked to myself for 5 minutes with the mute button turned on my microphone. I am I typically don't actually even use the mute function on this microphone, but I've been trying to get into the habit, and clearly I've gotten into the habit of muting myself, but not unmuting myself. So I will briefly go over what I've talked about for the last 5 minutes, apparently to myself. But good news is it wasn't really all that much. So we're doing chapter 2 today, and if you're new to this live stream, this is part of what I was talking about. If you're new to this live stream or you're watching this video on YouTube, this is basically just like a sort of 1 to 2 weekly, like weekly or bi-weekly stream that I do typically every Saturday. But might change. But that's typically the time where I go through a section of a technical book, and this is just a way for me to effectively give myself some accountability for reading technical things. And staying sharp in terms of consuming that kind of information. This book, the one that we kicked off in the last stream, is Systems Performance by Brendan Gregg, and I will go ahead and just show that. If you have this book, great. I recommend that you do. I recommend that you follow along because again, these streams are not intended to be sort of a regurgitation of the book, but rather just like an actual book club. Imagine a book club that actually reads the book. So that's the intention here. And so what I'll be doing effectively is going through and sort of picking out little pieces that I found interesting, maybe giving some anecdotes about my own experience. I do have a good amount of experience in the area of systems engineering generally, but I've never focused explicitly on performance engineering. That's always been a function that I've been aware of, and might be sort of like I might have a relationship with teams that focus on that, but I typically have not had that focus myself. So something I've always wanted to sort of like focus on, not necessarily in my day job, or at least maybe not right now, but just sort of understanding the principles and the methodologies and the tools behind the scenes, and that way I understand it more formally rather than picking up little anecdotes here and there. So that's the intention for me. Hopefully it's useful for you. Today is chapter 2. So in the last stream we covered chapter 1. That was the sort of introduction, and it was, as you might expect, a relatively short chapter. It covered a lot of different things with actually a surprising amount of detail for an intro chapter. But I'm sure that it goes into way more chapter throughout the book. I'm looking forward in particular to the CPU and memory chapters. Those are going to be epic. But things like just terminology in terms of like what even is performance engineering, how do we measure it, things like latency, observability, metrics, tracing, all that kind of stuff. So chapter 2 is about methodologies. And I found this interesting because actually a lot of what was covered in chapter 1 was at least mentioned again in chapter 2, but actually at a somewhat higher level. But it kind of makes sense if you think about it, because I think Brendan's intention was effectively to set the stage for some of these terms and give you enough of a definition of some of these terms before having to dive deep into them, which is going to happen like much later in the book. But in chapter 2, he talks about sort of the methodologies that are used to triage issues, troubleshoot them, find the root cause, what have you. And it'd be really difficult to wrap your head around some of the specifics there, or even the examples that he gives, if you don't know the very basic high-level definitions of some of those terms. So I think that's interesting. That this chapter will definitely sort of redefine some of those terms, or at least recover them, I should say. They'll have sort of a repeat, but obviously I think the future chapters will definitely dive much more deeply into them. I'm considering this more of like an intro to this sort of more soft skills kind of thing, where you sort of like have an idea of like the components and the tools and some of the more technical terminology. Methodologies is like, well, here's how you conduct yourself, so you make sure that you actually know how to like use those tools in the most effective way beyond just their syntax, which is really good, and something I think is definitely underserved. A lot of folks know how to read man pages. They don't necessarily know how to stitch tools together, or in what order to read them in, or the right questions to ask. That's I think the stuff that's less obvious. So it's good to have this covered. Okay, so I am going to go into. I have one more housekeeping note before I get started. Fortunately, not nearly as much housekeeping as the first stream. Being the inaugural stream, it was a little much. This one's a lot simpler. The one housekeeping note that I will offer, and let me switch to my screen share briefly, is I mentioned this at the on the last stream, I have a GitHub repository for the book club. It will be for all books, and so you won't have to bookmark multiple GitHub repos if we go into hopefully when I get into a new book, there'll just be a new directory. Now the intention here is not again to capture like everything in here. This is sort of just like artifacts on my machine that I created either during the live stream or in prep for the live stream. So you'll find things like little user space programs that demonstrate some kind of like bad behavior that we're troubleshooting. Or in this case, you see there's some Terraform files in here. This is where I've defined a Google Cloud VM that I spin up to actually demonstrate some of this stuff. So things like that. It won't be like, again, it won't be something where you can download this whole thing and you can, understand the contents of the book. It doesn't replace the book. And in the same way that these streams don't replace the book. This is just something that you can use to sort of augment your learning, certainly from the more hands-on and practical side. But it'll be aligned with the book in that the chapters that are covered will be contained within the streams in which those chapters are mentioned. At the moment, I'm just labeling it Stream 1, Stream 2. So basically, if you know the number of the stream, which I put in the YouTube videos, then you'll know which directory to look at. But I reserve the right to change that. It could become more useful depending on how we break up the book. That I might want to just create directories for different chapters. But I will revisit that and do relevant redirects as necessary. Okay, without further ado, let's get into, I'm going to pull up my notes like I did last time. Oh, interesting. My terminal is not updating. Let me see if I can fix this, actually. Interesting. I think what I ended up doing was I hit stream before I had moved some of these things over to this monitor. I'm thinking that's it, but yeah, anyway, it's working now. Yeah, make that a little bit bigger. Okay, so let me pull up my notes and we'll go through, starting with page 21. And 21 is the actual start of the chapter, so that makes sense. So let's see. I found that the observation I made in the last stream is I'm going to repeat here, and that is it definitely seems that folks that have a focus on performance engineering have a lot of sort of built-in instincts that I'm sure are at least in part built just by battle scars. It happens. But I think the nice thing about this chapter is it kind of gives you a framework for kind of inheriting those battle scars in a formal way because it's been distilled down to a set of approaches and methodologies that you can use to apply. And it's not just one, right? Like there's several, and we'll get to them. The one that I think is probably the most famous, if like I had to guess, just because it's of all of the things that are covered in this chapter, I have actually heard of the use method before, which we'll get to. But there's a bunch. There's surprisingly a large number of other methodologies in here that Brendan lists. He includes other things in like the models section that are brought in by other folks. And so I really get the sense that this chapter is there's a lot of thought put into this chapter in terms of gathering best practices from not just one person or even one company. Certainly, Brendan has tons of expertise to offer in this area, but he went through and actually included other things from other people. So really, really good chapter to start with. And I have a note actually at the end, but I'll just say it now. Especially with especially when we get into some of the trade-offs in the middle of the chapter. Honestly, the thought that I had was that this would be a really good chapter to read if you are prepping for a systems design interview. Perhaps not the only thing that you should read, but because of course it's not focused on like systems design interview prep. But a lot of the concepts in this book, I've had systems design interviews and conducted them where a lot of the concepts in this chapter were used. So you could do worse than to read through this chapter, so that you can understand some of the trade-offs. So that is sort of my initial anecdote on page 1. He mentioned he was sort of giving, or my thoughts on page 1. He was giving the anecdote about learning a lot of these things, watching over the shoulder of a senior admin or an engineer, and that's when I again was sort of like I had the thought of like, well, we've kind of received that experience through this chapter, at least as a start, which is really cool. Okay, great. So learning objectives also covered here. This is where we sort of get a taste for the use method is mentioned here, which we'll cover here shortly. We want to understand the thing that stuck out to me is it's mentioned quite a few times. Sort of like everybody talks about how to analyze a performance issue, but one thing that's mentioned here early on, and then even throughout the rest of the chapter, is when to stop analyzing a performance issue. I think I mentioned this in chapter 1, but this is worth reiterating, that not every performance issue is really a problem. If you've built a PC, even like you kind of have a general intuition for this, is there's always a bottleneck somewhere, and so some relentless pursuit of eliminating bottlenecks will eventually start to pay reduced dividends, and so it's a good idea to have your head on a swivel when you're looking into things like this, and ask yourself, is it like, for whom am I looking into this issue? I've had that moment several times actually at work, and it takes some time to really get a good sense for what actually matters. So yeah, so page 22 is where a lot of the terminology I mentioned from chapter 1 is sort of restated, but a lot of new things are introduced as well. I mean, things like IOPS. I don't know if IOPS was mentioned in chapter 1. These are input-output operations per second. So I typically hear about this for like disk operations. I've almost never heard of that in terms of like network sockets and things like that. Just generally, you just handle things at like how many bits are being transferred or bytes. But I/O per second is sort of like the rate of the number of operations, the number of discrete operations. And then throughput, response time, latency. The ones that a lot of these you might hear, but it's nice to see them side by side, so you can sort of be like, have that like at least renewed aha moment, because maybe you're not used to seeing them side by side. But like utilization versus saturation, it's just these are the perfect terms to use for describing how much a resource is used, versus saturation being it's used so much that actually it can't be used anymore. There's some constraint that it's hitting, and for that reason, work is being queued up. And obviously that's a hand-wavy kind of concept. What's being queued up and in what way, obviously totally differs based on the system. It might be that your system is just returning errors, and then there's work on a different service that's queuing up because it's seeing those errors, and it needs to store those operations somewhere. I think this is one of those things where it's very system dependent. And I'm used to dealing with sort of systems that work across like multiple machines, and so that's typically where I go. But it's certainly not the only way in which that can happen. Yeah, good terminology coverage. The models section was interesting. I'm not entirely sure I have my head fully wrapped around the reason that this queuing system is used. Obviously, the concept of a queue I think is straightforward, but I'm not sure. I had to reread it a few times, or maybe I need to reread it a few times. The section on queuing theory. This is just a very light intro. It's basically just a teaser. Section 2.6 is where it goes into that in more detail in the modeling section. I actually found the modeling section in general was the sort of the toughest part of this chapter for me. But we'll get to that. This is just like a teaser. System under test, I think, more straightforward. It's just the term that you use when you're sort of trying to understand the thing that might have the performance issue. Perturbations is sort of the term for things that could interfere with good performance on the system. Sort of thinking about like sources of these. There's a few lists here where I think the canonical example might be something like the noisy neighbor problem. You have another service on the same system, or maybe if you're in a cloud environment, you're running on a hypervisor, and another VM is running, and they're not. There's no hard allocations of system resources between them, and so a noisy neighbor problem could manifest there as well. But yeah, there could be all kinds of different things. I mean, the thing that always comes to mind, again, I'm much more used to sort of distributed systems where the problem for the system under test might be the system as a whole. But of course, if you break that apart, you're going to see things like, as he mentions, load balancers, proxy servers, web servers, things like that. And the performance problems that come up, or I should say the perturbation, specifically the interference that could result in a performance issue, might not always be obvious. It might be something that's more systemic and not something that you can necessarily see on one of those components. You sort of have to think system-wide. But yeah, something to keep in mind. Okay, so page 24 is where I think things get a little less sort of. A lot of what came before is sort of like a summary. Again, like as I mentioned, the sort of the models and the queuing system was mentioned. That's all covered later in the chapter. So section 2.3, which is on page 24, that's where we get into just concepts, he says. The first of which is latency. Obviously very important to cover, and I don't want to take this for granted because I think latency is one of the things that I personally probably care about very much, because I work not only in system, like I'm not only a systems engineer, I'm also specifically focused on sort of like networking, and latency is obviously a huge metric for networking. Not exclusively though. Latency can certainly apply to things like fetching information from disks and things like that. But I think sort of conventionally, it's thought of as a networking construct. But even then, as he points out, like it's not as if latency has necessarily one definition even within networking. He has this visual, and I don't want to show the actual visual, but I can sort of draw a version of it if I bring up my whiteboard here. That's the best way to do this. This is the other thing I haven't quite figured out yet. And I promised myself I would look into a new whiteboarding tool, and lo and behold, I did. Sorry about that. Hopefully this works fairly well. I've zoomed out all the way, and I've increased the width of the stroke of the pen, so hopefully the dimension issues that happened last stream won't happen again. Point this a little differently. There we go. So the concept here is effectively we have an HTTP request, right? And so you have your server. Is this showing? Yes, very slowly, but it's showing. Okay. Or a client, rather. So you have your HTTP client. This is like your web browser, right? And then you have the web server. Then you want to make a connection between the two. So if you consider that an HTTP request needs to take place over TCP, obviously the first thing that needs to happen is the three-way handshake, so one round trip. And then you need to send the HTTP request, and then you send an HTTP response, and then typically for HTTP 1, that is the end of the connection, and so you'll have a closure. The server will close, and the client will send an ACK back just to make sure that's graceful. But yeah, you can see that there's quite a few round trips in just the simplest case. Now, of course, there's nothing prohibiting something a little bit more intelligent to happen, where the TCP session is kept open and more of a long running connection is used. Obviously, that's protocol dependent. HTTP2 is good at this. You can do all kinds of things with HTTP2, which is still based on TCP, but still there's some overhead associated with not only the connection setup, but also like acknowledging segments and things of that nature. So this is cool from like a component diagram perspective. But if we then say, okay, ignore the components and draw the actual time, you have the total time for that request to take. If this is time, right? So 0 milliseconds, and we'll say, 100 milliseconds, which is pretty high, but we'll just make it a nice even number. That the time, the percentage of that is not equally distributed across all of what we just talked about. There's a certain amount of latency, where this is the visual from the book, where let's say up to here, let's say 70 milliseconds, which again this would be really bad. But let's say this is the actual connection setup. So three-way handshake, and then the actual back and forth of the data, including all the TCP overhead for that, occupies the remaining 30 milliseconds. we'll just say app generally, so like any application level data that needs to happen. So this is an important call out, and I think that the point that he's making is that when you say something has high latency, and maybe I'm leaping here, but I don't think I am, because I think he's covering this for the reason of being specific about where the latency actually happens. You hear all the time, if you're even in this space like tangentially, you'll hear things like, oh, the app has high latency. Well, what does that mean, right? Like what does that actually mean? Typically it means somebody pinged it, at least in my experience, which really only tells one part of the story. It actually doesn't even really tell much of the story we just saw with the diagram that's in the book. It really just talks about one round trip time from a layer 3 perspective. So like if as an example, I might ping my domain oswalt.dev, and we get 25 milliseconds roughly, maybe a little less. Yeah, typically a little less to the IP address that resolves to. But there's a big difference between, okay, it takes 20-ish milliseconds for an ICMP echo reply to be received in response to an outbound request. There's a big difference between that and the actual time it takes for the TCP three-way handshake to be established to that same destination. Never mind like the DNS lookup that took place before that. Like what if the DNS lookup was really, really slow, and then once it resolved, the pings to the actual IP was really fast. Well, that would indicate a problem with our DNS system, right? Somewhere along the lines. And it's important to have that level of specificity. And then subsequently, the TCP three-way handshake isn't captured here. Ping doesn't use TCP. And never mind any application layer stuff on top of that. So I have this little curl snippet, and if you've never used these, I highly recommend that you do. Curl has all of these really cool built-in like sort of variables that you can use for reporting. And I'll just paste it in here and explain it. Effectively, what this does is it sends an HTTP request to my domain, but it also records separately each of these durations. And they are durations. So if you imagine, again, the start time is 0. Each of these will be set to the actual timestamp from 0 where each of these phases occurred. So you get the DNS lookup first. I mean, think of what needs to happen when you send a web request. You got to look up the domain first to get the IP. Then your TCP stack has to establish a three-way handshake. Then TLS has to go over the top of that, and then the actual HTTP request has to be sent and then received. And so these measure each of those 4. So DNS, three-way handshake, TLS, and then TTFB's time to first byte. So effectively, what was the very first time that we received the very first byte of the response? And if you run this, you can see they all obviously kind of add on to each other because they happen chronologically. DNS is very fast, right? That's not surprising. It's probably just using either a cached entry on the system or a cached entry on my DNS server in my basement. I can't remember which. But either way, very fast. The three-way handshake, considerably longer, but still pretty good, right? Like we're talking about around the same, what is that, 20, effectively 29 milliseconds, a little bit higher than the ICMP round trip time, so pretty good. TLS, a little bit more than that. And then finally, the time to first byte, considerably longer, but still pretty good. We're talking about a tenth of a second. So that's the time it takes to get the actual first byte. So not too bad. But again, like I think the important thing is not when you're talking about these concepts, there's so much to talk about. You can't get away with being vague. If you're saying something that has high latency, you have to think what is actually not only the specific component, but the specific operation that I'm making that statement about. He mentions, I think actually in chapter 1, and it came up in the quiz at the end of this chapter, but the concept of micro benchmarking. I may be misapplying the linkage between the two, but I think of that when I think of this. It's like you can't say that a given performance problem is on sort of the system as a whole. You have to break it down. And one of the methodologies has this concept of 5 whys, where you get to the actual root cause by keep asking why. So this is slow, but why? Oh, this other thing that it depends on is slow. So you keep going. Anyway, a little bit of a tangent, perhaps, but I found that to be I found this to be instructive in the indirect sense, where you're like, it's almost a soapbox for me. I hear the latency is bad all the time, but you could be saying that a bunch about all kinds of different things, and it doesn't help anybody to be imprecise there. Okay, so let's move on a little bit. Page 26, my note literally says timescales equals cool. So if you haven't read this, it's something that you might see on you could look this up probably easily. I don't think this is something Brendan necessarily like invented, but it's effectively trying to make the timescales that we typically deal with in computing something a little bit more reasonable. I'm trying to think of another example. I think this sort of the helpful scale that I'm used to hearing isn't about time, but actually distance. Because similarly, we talk about astronomical distances in the solar system, and then in the galaxy, and then in the universe. We just like throw these numbers around like we have any concept of what they mean. I think the same is true when we deal with performance engineering stuff, because we talk about things like nanoseconds and microseconds and picoseconds, and as if we can, again, as if we have like an intuitive understanding of what those times actually mean. We know their definition, but we don't necessarily like know. The sense of scale is sort of lost, and this table, I think, reapplied that sense of scale. So as an example, 3 nanoseconds for level 2 cache access. If that scales to 10 seconds, which obviously that would be horrible if it was actually true, but 10 seconds is something we can wrap our head around. With that same scale, something like a TCP timer-based retransmit, which that happens all the time when you deal with loss on a network, that would be roughly about 1 to 3 seconds. But to scale, that goes up to 105 to 317 years. So that sort of, and there's many other examples where similar examples are given with the same scaling. I thought that was really cool. So yeah, definitely check that out if you have not read that. So that's page 26. Okay, so real quick stream health check. Okay, yeah, not too bad. Not too bad. Page 27, I wrote a note, something along the lines of trade-offs. So this is the section on trade-offs. We've all heard fast, good, cheap, pick 2. He gives another one, high performance, on time, and inexpensive, pick 2. He makes the statement that many IT projects choose on time and inexpensive, leaving performance to be fixed later. And I could definitely imagine and even remember anecdotes where I've observed the same. But to be honest, the thing that came to my mind, and maybe this is just sort of a unique perspective that I've gathered, or maybe I've just worked with different groups of people. But certainly earlier in my career, when I did a lot more consulting, I saw a wide variety of environments. Both relatively large. I never saw anything as large as sort of what I'm working on now, but sort of the really the big sort of enterprise companies. I'm talking about like the petroleum companies or banks or things like that. A hospital or just anything healthcare related. They run the gamut. And in my experience, the trade-off actually is a little bit more nuanced. I've seen environments where performance definitely an afterthought, but I don't think it's necessarily even fixed later. Typically, the software that I've observed in these environments, it's just everybody kind of knows, but also accepts that it's crap. You might have like an electronic health records system. Maybe that's a bad example, but something like that where you need to use it as part of your job. And I'm talking about sort of not necessarily the technical folks, but the employees that are working at such a place where they kind of all just know that it's crap, but they use it, and so they just get used to it. And so like the stakes from a performance perspective are quite low. And then on top of that, I've also noticed environments where maybe the users are less forgiving of performance issues, but the vendor has sort of baked into their recommended architecture this notion of, well, just buy multiple licenses and buy our load balancer and spread the load across. And so these like inefficiencies that are baked in at the application level are just not incentivized to be fixed, because there's actually a financial incentive to not fixing them, because you can sell the Band-Aid along with it. And maybe that's it's been a while since I was in the consulting game, so maybe it's different, but my instincts are telling me that it's not. Either way, that is, I think, orthogonal to what we're talking about here. I think the point of this book is to give you the instincts to either think of performance as a first-class citizen if you are developing those applications, and hopefully you can get your leadership to justify your time spent on it. Or if, again, you are focusing on performance engineering as a skill or even as a discipline, as a career, then I think it's great. So let's leave those anecdotes in the past where they belong. So page 28, I think, is what we were on. No, we were on 27. So page 28 was the next page. Level of appropriateness. I just noted that. While he makes the statement, while the application, this is actually before level of appropriateness. This is still back on tuning efforts. While the application can be the most effective level at which to tune, it isn't necessarily the most effective level from which to base observation. Slow queries may be best understood from their time spent on CPU or from the file system and disk I/O that they perform. These are observable from operating system tools. And I think the reason I called that out was because I missed it in my notes, but I'll just say it now. Performance tuning is most effective when done closest to where the work is performed, because, again, it's like, as I mentioned, there are definitely cases where you can patch effectively a band-aid, a performance issue, with some like additional infrastructure, right? If the application performs okay when it's like 30% utilized, then say, oh, you need to do capacity planning that makes sure that no one application server is over 30% utilized, which, again, it's like, that seems like a low bar, but in my experience, again, a lot of enterprises are happy to throw more money at the problem to make sure that it works. And so the trade-off for me, in my experience, has been a little different, but definitely not saying that it's the right thing. It's quite depressing when that happens, but it happens. Okay. Page 30. I think actually I took a note on page 29. I said something about performance ROI. Right. This is where we get into. This is the section that talks about when to stop analysis. This is like one of the biggest lessons learned from this book. It's sort of just like, say, when do I actually stop? How can I justify the effort spent in digging into a performance issue? It's literally titled "When to Stop Analysis." So definitely recommend bookmarking this because it's a really good way to sort of. It's a shorter section. It's not exhaustive. I don't think it tries to be, but it's a good thing to keep in mind, even if only as a reminder that you should be thinking about ROI when you do performance analysis. I think that's the biggest thing that you can do, is just remember. We all have to make these decisions in our day-to-day, justifying the time we spend and making sure that we're spent focusing on the things that are most impactful. If you get so laser focused on eking every little picosecond out of one particular function call, you miss the forest for the trees. Actually, that brings up an anecdote that I didn't even write down in my notes, but I do remember working with somebody who was very laser focused on trying to improve the time complexity of some function. Which I'm sort of two minds there, because I think both of us were fairly early in our careers anyway, and there is I don't want to certainly don't want to make fun of that kind of mindset, because I think of the two, where I see somebody who just doesn't ever care about this versus somebody who might care too much, I'd of course choose the latter, and I think most people would agree with that. But in this particular case, they were thinking really, really deeply about a particular, function call. But it turns out, due to the design of the application, that function was only going to be called every 30 seconds, like literally every 30 seconds. It was some sort of like batch job, and it's not as if that function was called in like a loop or recursively or anything like that. He was literally shaving, nanoseconds or maybe a little bit more, but very small amount off of something that literally only happened once every 30 seconds. So it's good to, again, keep some perspective, because there might be another performance problem that you could turn your attention to that would be much more impactful. So yeah, ROI is important. I'm gonna hydrate real quick. And even though there's a light on my microphone, I'm going to real quick check audio levels just to make sure I'm still audible. Okay, great. And also a time check. 55 minutes. How about that? Time flies. Well, I think I ate into it. I think I ate into the time by about, 15 minutes, I think. Yeah, today was a slow start. Page 30. Architecture. I wrote a note. Oh yeah. So load versus architecture. Yeah. So again, I'm a little biased to think more about distributed systems performance. That's obviously not the only place you should be thinking of this. I think Brendan, I believe, covers sort of that, and like he covers performance generally. I don't think this book is necessarily focused on one or the other, but a lot of my anecdotes tend to be more distributed systems because that tends to be my my expertise or background. But I'm reminded of an anecdote where I was dealing. I have sort of like it's a system that does HTTP redirects, and in a way that I won't get into. But effectively, it uses HTTP literally like 308 responses to redirect from one resource to another. And the contents of that redirect does something specific to the system, but that redirect is handled at a place in the system where it's actually really inefficient. If it was handled elsewhere, meaning like if it was intercepted by a link in this chain of systems, which it can be, and then the redirect was actually followed earlier on, it would actually improve the system performance by a lot. And if you look at like the HTTP stack, where you're like, okay, how quickly are we parsing the HTTP response? How quickly are we serializing it to some socket, right? Like if you just look at those things, you're going to miss the forest for the trees, because truly the improvement comes from an architectural change. All of the nodes in the system are dealing with their the HTTP serialization perfectly fine. There was really no problem there. It was actually built into the architecture that the problem existed, and this was something that wasn't obvious when the system was first deployed. It actually wasn't even a problem when the system was first deployed. So this is the other thing. Is like you have to stay on top of these things over time. Assumptions that were made early on in the lifetime of a system might change. So yeah. I wanted to share that anecdote because that's what stuck out to me in terms of architecture. Yes, there might be a bug in an HTTP parsing library that you might introduce via a release, or it might be triggered via some edge case. But you also might encounter it just in the normal day-to-day operation. But maybe the architecture has some sort of design flaw in it that's sort of latent. That's what came to mind in that section on page 30. Page 32, this is where we get into metrics. So, yeah, this was kind of covered briefly in chapter 1, and forgive me, I'm just going to go back real quick to see what was shared there. Okay, counters, statistics, and metrics. Oh, right, I remember covering this. Yeah, he gives like the output of VM stat. These are sort of counters for a variety of things. Back to chapter 2, this section on metrics dives into some specific examples of metrics that are useful. Throughput, this is operations or data volume per second. IOPS, I/O operations per second. The difference there being effectively, throughput. You're sort of measuring. You're measuring the data itself. IOPS is more sort of how many, like, I'm trying to think of a specific example, but if you might think of like IOPS being the sort of number of times you've read and written from a disk, we'll make that very practical. But if IOPS is very high, your throughput might not necessarily be high, right? Like if you're only reading or writing a very small amount of data for each I/O operation, your overall throughput might not be very high. So the two are kind of related, but they don't necessarily, like, one doesn't cause the other. You have to sort of break the two apart. And then, so, of course, in like the networking example, again, IOPS is not typically a term that's used within networking, at least in sort of the areas that I use. Although there's no reason it couldn't, I suppose. It would just be kind of like a weird, almost forced synonym. But but throughput certainly is. Like throughput is obviously used in networking, where we say literally the number of bytes that can be shoved into either a physical connection, right? You're talking about throughput, literally data that's being sent on a physical medium, or you might be thinking of throughput in terms of like, okay, in this particular like TCP session, what's my throughput? Because then you have to take into account things like the bandwidth delay, product, and things like that. So yeah, throughput is sort of like just more of a volume of data per second. And then again, utilization, I think this was covered earlier on, but utilization, and then there's also saturation. We're definitely going to cover that later on as well, but utilization is how busy a resource is, as a percentage. Latency, we already talked about that, and we're going to talk about it again. Another good example of a metric. Now, I have an example later on where I bring up actually a Prometheus instance to talk about metrics, but I'll save that for later because I think Prometheus literally gets used in the book later, at least as a sort of side thing, but I'm not sure to the depth that it's explored. I think it's much more about like what Prometheus would be perhaps scraping. If you don't know, Prometheus is effectively like a metrics. Well, it's a bunch of things, but it's primarily a way to gather and display metrics in a time series format. So sort of time series database. There's the ability to sort of scrape metrics from something, which will again I have an example to show that. It also has alerting built in, and there's all kinds of other things too. But I'm trying to keep it simple. Because again, I don't actually remember to what extent Prometheus is covered specifically in this book. It may not be. I don't remember. The demo that I have, it's definitely not worth all of the effort that it seems like it is. It's a very simple demo. So actually what I'll do first is I will show, what are we in? Stream 2, and I think I named it high CPU. Perfect. Actually, yeah. Stream 2, high CPU, perfect. Okay, great. So you can sort of see the project structure. It's just a Rust program with a main.rs. Real simple. The general idea here is showing effectively an example of what's originally came up in chapter 1. I actually built this last week because I was going to show it in that stream, and then I decided against it. So this is just showing it here briefly, but this is a good example of an application that will give you metrics. Now, this won't insert those metrics into something like Prometheus, but you certainly could. But this is an example of an application that is designed to just keep the CPU busy so that we can see the effect of that. So yeah, this is the VM that's in the repo. Again, if you want to follow along, the VM that I'm in is literally in the GitHub directory for this book. It's book specific. I'm gonna create other VMs for different books, I'm sure. But this one's specific to this book. This one, there should be commands that you can use. I'll put it in the README. And one sort of programming note, I actually haven't updated this for Stream 2 yet. You'll notice that it's not even there. But I will after this stream shortly. So if you're watching the recording on YouTube, I will have already done this. But if you're watching the stream before that, then apologies. It's not quite there yet. So just stay tuned for that. So for this, I have... let me scroll back up to my notes on that. So in the book, he talks about VM stat. So let's run that, actually. VM stat. And then that will record metrics on, or it will output metrics on the CPU utilization on the system as well as memory. But the CPU utilization is really all we care about. High CPU is the program that I have uploaded to this VM that just keeps the CPU busy. And I could have sworn that I actually uploaded it, and I totally didn't. Let me do that real quick. Let's see, where was that? I'm pretty sure I've compiled it, but that might not be the case. Let's at least go to the directory and see. Stream 2, high CPU, and then... where is it? Oh, target. That's right. Target. You know what? I'm actually sure it's there. I'm just going to try to upload it, and if it's not there, it'll obviously fail. So let's just do that. So this will SCP the binary to my VM. Perfect. Great. I must have deleted it on the VM for some reason. Oh, I know what I did. I recreated the VM. That's why. Okay. And then, yeah. Let's get back into it. So again, these metrics have been reported for a while, and again, this demo is now totally not worth it just because of how long it's taken. It's still kind of contrived, but still useful, and certainly you can run this on your own if you'd like. But if we run high CPU, what this does is it spins up threads for whatever you specify, and it defaults to one thread. So obviously this isn't going to keep the system all that busy. You'll notice that it's sort of oscillating here between 100 and 50, and it sort of settles in there. So we're really not waiting on anything here. And the R value here is supposed to be equal to the number of CPUs. Now, if that grows beyond the number of CPUs, that's when we know we have saturation. So utilization is sort of like how busy our system is. And just to break this up, you can say like we don't have HTOP installed. I gotta automate some of this stuff. It was installed before I recreated the VM, but either way. HTOP is just a little bit easier to see some of these things, but top's fine. You'll see that obviously the bulk of the CPU activities coming from our little high CPU binary. But VMstat sort of reports that there really is no saturation. So utilization, sure, not saturation. But we can pass, I think if I remember the code correctly, it's just a single parameter where we can pass in, say, like 2. And that'll create two threads. And now we are actually we are saturated because we're reporting an R value of greater than the number of cores on the system. So yeah, anyway, probably not worth all of that effort in terms of fixing all of the things that I forgot to do for setup. But either way, there you have it. That's a demonstration of utilization versus saturation. So great. The continuation with page 35 is where we get into profiling. It's just, I think the note for me is this is something I'm a little weak on, so it's something I want to get into a lot more. It's just something I don't often reach for, but I should. The next thing is on page 38. This is a reminder from chapter 1. This is a breakdown of the difference between workload analysis versus resource analysis. So if you're an application owner, you might be sort of inclined to think about metrics from the perspective of your application, right? Where you say, oh, well, I have this system that makes web requests, and so I'm going to measure time to first byte, as we saw earlier. That might be a good metric to look at. And you care about things from that perspective. So you might have, again, an app, and like if you're making HTTP calls, you care about those things. So like time to first byte is a good example. Time to first byte. This is the workload analysis. It's really just a description of perspectives. But then, of course, underneath the app, you've got system libraries, then you've got system calls, and then the kernel, and then hardware. And of course, there exists the opposite perspective, where it's resource analysis. Now, I think he mentions this in the book. Both are valid. It's not meant to sort of say one is more important than the other. And actually, it's good to be able to do both. And the reason for that is it actually comes in handy later on in methodologies when we talk about things like being able to define the problem statement very well. For instance, the actual problem might be something in something that only the metrics gathered, or maybe the trace points gathered at the kernel level, can really illuminate. Certainly the symptoms will be felt at the application level, but it could be useful to actually start from the resource perspective so that you are actually exposed to the real symptom much earlier. I'm getting a little bit of dropped frames now. Just double checking on that to make sure it's nothing I can do anything about. I don't think so. But yeah, apologies if you're watching live and the stream suffers. Hopefully the recording is fine. I'm only seeing network drops. So my service provider has had issues lately. I'll just leave it at that. I don't think that's a strange concept to anybody in the U.S., but yeah, that is definitely something I'm feeling. So page 42. Did I skip over pages? No, I don't think I did. I think I might have been turning pages sort of on autopilot. But yeah, these are where we get into methods. Methods is I think the sort of the center of this chapter, because the title is Methodologies, and section 2.5 is methodology. So not surprising there. A lot of different tables that are covered, or tables to cover a bunch of different things, where he defines sort of the different methodologies, or he lists the different methodologies and the kind of analysis that they involve. But then, goes into each one shortly thereafter. Lists a few, he calls them anti-methods. These are, anti-patterns, but anti-methods. Things you should not do, or things that you might do if you don't in the absence of a better methodology. The streetlight anti-method was effectively, you don't really have one. You kind of just poke around until you see something that's interesting. And usually that doesn't really yield results. The random change anti-method, I am definitely guilty of. Certainly from like a local development perspective, where I'm not really, again, like sometimes catch myself not turning my brain on fully, and so I'll just kind of like try a bunch of different things, but there's not really a rhyme or reason for them. I'm just kind of like seeing like, maybe this works. It's just not the way to go. A structured approach is definitely better for everybody. So the methodologies, there's several listed, and I won't go through them all, but the ones that I'm going to call out are going to come in handy towards the end. Problem statement is one that you should definitely read. This is something where effectively it allows you to frame the investigation, but then it actually provides a way where you might actually find the issue on your own. So asking questions like, has something changed recently? Huge one. I mean, absolutely huge. It's something that I use at work all the time, where there's just like a series of not only questions, but just sort of, I mean, I guess that you could make them questions, but things that I would like to know at the top of any investigation. And and one of the things, I think I mentioned this last week, one of the nice things about the sort of rise of these like LLM based tools is actually, in my opinion, the one of the strongest value is on like initial triage for things. So if you have tools that can go fetch metrics or fetch other things, diagnostic information from systems, maybe you've got it wrapped in a script. Feed that script to the agent of your choice, and have it just do initial triage for everything. The best shops will have SOPs for initial triage, where you have a set of commands that you can run, put that in a markdown file, and then have an agent execute them on your behalf. I think that's all positive. But the problem statement methodology, I think, is that, but also just in general, asking the best questions that you can to know that you've fully wrapped your head around the details of the problem. Are there specific ways in which this problem is manifested? I was looking into an issue recently where there was a particular tenant. My service operates, in a sort of I should like a multi-tenant kind of capacity, whereas there's different other internal things that use it for different things. But one of the most important questions I asked was, is this performance issue a problem on all of these tenants, or is it just one that's causing this? Or are there symptoms of the issue, or maybe trailing indicators of the problem that are tenant specific? So these are great things to ask, because again, either like best case scenario, it helps you just diagnose the issue right away. Maybe it's something you've seen before. But even if it doesn't, it's all really good context for the investigation that follows. So it might rule out an investigation entirely, but if it doesn't, it's still great to have all these questions ready to go, these answers ready to go for an investigation. Really important. Next one's the use method. This is sort of, I think, the bread and butter of the chapter. It's the one that I've heard before. It's probably one of the more famous ones from the book. This is utilization, saturation, and errors. So if you go over to page 48, you'll see that it's actually more of like a decision-making flowchart where, again, I'm not trying to sort of regurgitate the whole book here, but it's worth calling out, because again, it's kind of core to the book. But here. So in a very simplified view, we have I'll just draw a simplified view, but it's a flow chart. You're saying, okay, let's go in, let's identify a resource, and I think this is really important. Coverage of what we talked about earlier, where it's really important to be precise. So if you're saying something like, okay, is latency really bad? Well, what are you talking about? Let's narrow it down to the specific resource. That might not be exactly what he's talking about in this. But oh yeah, no, there's a resource list on page 49. So a better example, I guess, would be like literally resources. So CPU, memory, network interfaces, storage devices. Gather metrics from those. And then the actual use methodology is in reverse. Actually, it's if you follow the flowchart, it's E, then S, then U. Where the first thing you do is you check errors, and the logic he gives in the book is if there are errors being reported, that can be really specific. You can actually use those to really narrow down where the problem is coming from, because they're pretty explicit, and generally they should be pretty rare, right? You should be operating a system that generally doesn't fire errors unless there's a real problem. So if there are errors, hopefully they stand out. So that's why those should be checked first. And then you sort of progress down this flow chart. If any of these yield yes, you go over to diving into like that specific thing. But if there are no errors, then you go into sort of saturation, because maybe there are no errors, but there still might be some indication where work is queuing up, or some resource has hit its limit. I have an example that I'll cover later on file descriptor usage. So it's a really good idea to limit the number of file descriptors that a given service can use. There's ways to do that in systemd. And I have many actually anecdotes of a service reaching its file descriptor limit, and so when that happens, it literally can't open up any more files or do any syscalls that would result in the creation of a file descriptor. So yeah, that might be happening, and like typically those might surface in errors, but they may not be, right? Like you might have an application that performs some sort of operation that reads from a file, but it might be sort of like, maybe optional. And so it might not log any errors. I'm kind of pulling this out of thin air at the moment, but yeah, I can imagine scenarios where saturation can be present, but errors may not exist. I imagine that with file descriptors, it's probably less likely. It's probably more likely with things like memory usage or CPU usage, where it can kind of degrade a little bit more gracefully while it's saturated, without anything really having like a hard error. So maybe that is a better example. But anyway, wrapping this up, then you have utilization. So if there's no saturation, then you look in utilization to see what resources, at least look at their utilization. Nothing saturated, no errors. Let's at least see what the utilization looked like. Then you can do things like tracking that over time. So maybe nothing saturated, but there's a huge spike, say, in like the amount of memory that a given service used. That can be, at the very least, a breadcrumb to follow, even if nothing's saturated. Even if the system has free memory to spare, it might yield some interesting next steps. So yeah, that's the use methodology. The other one that I'll mention is workload characterization. I briefly mentioned this in the anecdote I just shared, but I didn't name it. So workload characterization is, I think, in my experience, really useful for doing things like, okay, like are there specific aspects to this issue that are unique? So the examples he gives in the book, like who is causing the load, process ID, user ID, remote IP address. In my anecdote, it would be something like a system is listening on, say, 10 different sockets, network sockets. Maybe the problem is only happening on one of them. That would be a good thing to narrow down. So yeah, just effectively characterizing the specific nature of not necessarily the problem, but the interesting things that you've seen via the other methodologies like the use method. Page 56. I found interesting at the end of that section that started on the drill down analysis, which started on page 55. But 56, he calls it the 5 whys. This is also really helpful because I think, again, it's sort of like the methodology behind solving the latency issue that I brought up earlier. Again, you might say, he gives an example in the book, but so definitely use that. But I'll go off of the example that I gave before, where you have an HTTP request that's slow, right? So let's draw the timeline out again, where you have the timeline for an HTTP request. Let's say it's really bad, like 400 milliseconds, right? And then you say, okay, that's really bad, but why? And the reason that's important is because you have no way of identifying like the root cause of this, and if you don't have the root cause, then you can't possibly fix it. So is the problem in the actual the client, right? The web client or the server, whichever end you're operating. It's assume that you have insight into both, perhaps. But you still are gathering this metric probably from the client's perspective, where it's measuring the time it took to get let's say time to first byte. Let's keep this as real practical, where you say time to first byte is 400 milliseconds. Pretty bad. But again, if you just look at that, you don't know. You can't begin. If you keep your perspective limited to that and you don't ask a follow-up question, you can't possibly hope to figure out what the actual issue is. At best, you might make assumptions. You might say, well, it's definitely the web server that's slow. But you don't know that. You just don't. And I'll give an example of how you might not know that. So for instance, it might take 350 milliseconds to do the three-way handshake. I can't imagine why, but let's say there's a lot of loss on the network, so the three-way handshake doesn't actually complete until much, much, much later. That's sort of a contrived example, but let's say maybe a little bit more realistic. Let's say the three-way handshake completes fairly quickly, right? So you say like three-way handshake. But there's enough loss on the network that you are trying to make a request, and let's say you make the request pretty fast, so request, but the payload is really big, and there's no pagination or anything. It's sort of like a 300 megabyte response, and you kind of have to get it all in one go, and it keeps getting interrupted at the TCP level. So the actual socket doesn't get torn down, so your browser or whatever it is, your client doesn't say, okay, this failed. But TCP keeps trying to retransmit data because it keeps getting lost. That can add a lot of latency to the overall request, and so maybe this is all TCP retransmits. These are actually network causes where the web server is operating perfectly fine, but the actual network that's transmitting this application data is performing poorly. If you don't ask that follow-up question of why, you won't get there. So really important to do that. Great. Let's see, time check, 2:27. I might actually skip a few things. I don't have a ton left. Let's see. So I will. So one thing I will do. I just covered drill down analysis. I did take a note on modeling, and I don't mean to diminish the chapter or diminish the section. In fact, I'm quite positive that it's just above my head. I was able to follow it to some extent. But a lot of the modeling, like the different laws and things like that, I'm gonna have to reread that a few times. Yeah, we got into queuing theory again. I think I mentioned this at the top. I'm aware of what a queue is in terms of the data structure, but I think I'm gonna have to reread this a few more times to understand the value here. Again, I think I kind of understood it as I was reading through it, but I wouldn't feel comfortable trying to regurgitate it. The one thing I will call out, and I had a note to like actually draw this on my whiteboard, but I'm going to skip it for the sake of time, is the scalability profiles on page 64. So this is where we might see things like a linear growth in terms of resource utilization or throughput or what have you. Then there's contention, where like the more load you put on a system, the slower the actual rate of increase, the lower the rate of increase. There's also coherence, where you might have, as load increases, typically you might see this with like lock contention, where as load increases, you actually plateau and then actually go back down, where literally your application has turned into a lock contention system more than actually doing work. Then there's also like knee points where some sort of constraint is hit, and then there's a new bottleneck that slows things down. It's not quite a sharp knee point, but it's a rounded one. And then there's ceiling, which we actually will see. I have this in my demo at the end. Ceiling is, I think, more indicative of like saturation, where you are using a resource up into a point, and then all of a sudden you've hit like some sort of really hard enforced limit. So anyway, I highly recommend that you read through this. I certainly will be. I found the contents of the section interesting, but I just didn't have the ability to go through it and with enough comprehension to say anything meaningful about it on stream. So I'm actually gonna skip ahead to let's see, page 70. Brief mention there. Resource limits, definitely worth covering. So this goes into things like I think the call out that I want to make here is your system has resources other than CPU and memory. I've covered file descriptors. In my experience, file descriptors, I knew of them when I was early in my career, but certainly didn't get until I started really running important's not the right word, but production systems that have a certain scale and I'll say performance requirement that I actually had to start caring about those about file descriptor usage. And so that's something that gets underserved. There's a lot of other resources that are listed there that I think are also worth looking at. Disk throughput, I think, also kind of underserved. Like, everybody thinks of capacity, like how much disk space am I using, but like how are your disks actually performing? What are your IOPS? Things like that. If you're doing a lot of operations on disk, then you definitely already care about those things. But if you're not exposed to it, you might not realize that. Okay. Page 73, statistics. I have a lot of notes here, but I'm going to try to be a little bit more summarized. But this is actually sort of towards the end of the chapter, so I think I'm okay on time. I don't want to go past the 2-hour mark. I would like to stick with more of like a 1.5 hour is sort of the sweet spot. But actually, given the way this stream started, I'll be editing out a good amount of the first little bit. Anyway, and just in case you're wondering what I'm going to be editing out, total silence. My microphone was muted. So I spent the first 15 minutes just trying to fix a hardware issue, and then I actually joined with my microphone muted. So I wasted a good 20 minutes. That'll all get edited out. So if you're watching the Twitch stream, unfortunately, you're exposed to all of that. Apologies. But if you're watching the YouTube video, hopefully it's not too bad. I guess by my estimation, we're about 1 hour and 10 minutes into the YouTube video. So we're in a good place. Let me real quick get some water. Okay, so getting into statistics. The most important ones to cover are, I was going to draw this, but actually I'm going to see if I can find a more sort of legible example online. Yeah, maybe I will just draw it, actually, to be honest. Yeah, that's not too bad. Okay. There's an example in the book anyway, so I might as well just mimic that. I just didn't want to make too much of a mess on this diagram. I'm trying to rely on it a little bit less than I otherwise might, just because I haven't figured out a way to make it as legible as I'd like. I'd really like to have something with a dark background, but as I found, this freeform application on Mac doesn't even allow you to do that. You have to do some like weird tricks with adding a black rectangle behind the scenes, and then like making sure you don't pinch the edges or something weird like that. I didn't want to mess with all that. That was too much. Okay, so if you've ever seen a normal distribution, this will be nothing new. But I'll take the example from the book and I'll make it a little bit more realistic, or a little bit more relevant to the specific example that I'm going to show. If you have, let's say, the y-axis is the number of measurements. He says counts in the book, but measurements. And then the y-axis, or x-axis rather, is latency. This is a distribution of latency measurements. So imagine we're running... Let's imagine we're running a system where we're performing latency measurements, and again, what we're measuring, it depends, but you should be thinking about that. Like, what is latency of what? We could be talking about anything though. Like this could be HTTP latency, latency of, like, again, time to first byte is a good example of latency. The latency from the actual the beginning of the operation, meaning before the TCP stack is even touched, time to first byte, the latency to that, and that could be what we're measuring. But we'll keep it more abstract for now. What you might imagine seeing is if your application is performing this measurement from, let's say, 100 different servers, and you plot all of those on some sort of a graph, you'll end up seeing a curve similar to this, or you'd have to plot it in this way. So if you're using the y-axis of like the actual latency, it's different. But the distribution of those measurements is going to it could follow something like this normal distribution, where you have some sort of a mean, right? This is the mean or the average, where most of the latencies tend to center closely around that center. And then if you make the curve narrower, then they're even more tightly clustered around that. If you make it wider, then they're a lot more spread out. Then you'll have, this is like 1x standard deviation. So stood, and then down here, I didn't quite get close to the bottom here. But then you start to think about things like percentiles. So what is the measurements that are above the 99th percentile? And there could be none actually, but there might be, or there won't be none. But there could be perhaps one, right? It just depends on what it is. And how many measurements are above that. But yeah, basically the percentile measures, okay, like what's out here? Like what is my 99th percentile? What is this latency value where 99% of the measurements are below this and 1% is above it? So again, it's percentage based. And then, of course, you have the min and the max, where eventually this curve literally ends. So that's the min, and then I kind of screwed up the max, but it's at the end there. So that's really important to know. Percentiles come in handy. Because there are certain things that if you just do the average of a measurement or of a series of measurements, then it could paper over things. But of course, sometimes it's actually preferable. We'll get into examples of that in the example at the end. The other thing I want to bring up is histograms. This is on page 76, and fortunately, Brendan has an image very, very similar, not the same, but it's very similar to what's in the book, and I'll bring it up over here. So this is a histogram showing disk I/O latency. You'll notice it actually doesn't look that different from the curve that we just showed, but it is different in that it actually shows a multimodal distribution. And this is something that's covered on page 76. So you might have two code paths where the latency and both code paths are doing disk I/O, and one of those code paths might be quite fast and the other one might be quite slow. And a histogram is really good at capturing that. And in a production environment, like if you're using Prometheus, what you would end up doing typically is you would define buckets in the metric that you export. So in Prometheus, or rather in like a Prometheus client, you'll say when you define a metric for your application, you effectively define these like ranges where certain buckets should be, and then usually at the end there's one called INF plus, which is just capturing like everything else. So you say like if I have one bucket, it looks like there's buckets maybe perhaps down to the 10 nanosecond scale, where this is a bucket of 10, this is a bucket of 10, this is a bucket of 10, and they go between 500 and 1,000. Or something like that, I'm guessing. But then the histogram shows effectively the frequency that certain disk I/O operations took place within each of those buckets. And so if you've got a much more normal distribution, you'd see the histogram would really be centered, like everything would be clustered around this. But here it's kind of spread out, and it sort of indicates that you have two code paths. If you again deal with just averages, or if for instance you took even percentiles, like if you showed the percentile, you'd see more of these, but you'd sort of paper over a lot of this. It wouldn't give you a sense as to the actual distribution of the measurements. So histograms are important. I'm sure they'll come up later, but I've made good use of histograms in my work as well. Okay. I'm going to take a pause here. And I don't love to do this on stream, but my mouth is getting crazy dry. Just a quick check of stream health. I was dropping some frames a little bit ago. Yeah, man, 4.8% dropped frames. But again, hopefully the local recording is much better. Yeah, some additional visualizations, which are cool. So exercises. Yeah, exercises at the end of the chapter. I'm gonna skip. I'm gonna sort of briefly mention the terminologies. What are IOPS? What is utilization? What is saturation? What is latency? What is micro benchmarking? The top four were covered many times in the chapter, but actually the micro benchmarking I had to remind myself on. I thought I knew what it meant, but I think I had it wrong. I was thinking about something else. Back on page 13, actually, in chapter 1, is where micro benchmarking is first mentioned. This is it's sort of the concept of testing a specific component. So again, it's like if you think of macro benchmarking as measuring the time to first byte for a request, I think that could be a good example of a macro benchmark. I think perhaps that also would need to be coupled with a synthetic request. So maybe not measuring real metrics, but like reproducing a request via some sort of synthetic request instead of looking at like production traffic, and then measuring that. But then micro benchmarking would then say, okay, let's do the same thing, but actually measure like one really specific part. So just give me the TCP round trip, right? Ignore anything to do with layer 7. Let's just focus on TCP. So something to think about. But that's the only term I think I had to remind myself on in the end of chapter exercise number 1. End of chapter exercise number 2 is where things get kind of interesting. I sort of I'm going to cheat a little bit, and I've mentioned file descriptors a few times. I suspect there will be decent coverage of file descriptors later on, but I'm going to cheat a little bit and dive into them a little bit more because I was trying to think of an example. And I have actually for a couple weeks, trying to think of an example of a performance related issue that I've experienced and that I could apply the use framework to. And so this is sort of what I came up with. One of the things that I deal with a lot is file descriptors either growing disproportionately to sort of input, like traffic, right, to a system. Maybe there's like an inefficiency where you might hold more file descriptors for a given operation than you might need for various reasons. There's also the concept of a file descriptor leak. So every once in a while, you'll have a system that literally loses track of file descriptors. Typically, that's a bug, something you should fix, where the actual application kind of forgets the file descriptor that it has asked for, but hasn't given it back, hasn't closed it, and so the operating system thinks, oh, you're still using this, but it's not, and it can't because it literally has forgotten it. So that will obviously, if that keeps happening, number of open file descriptors will inevitably increase, and the rate of increase depends on all kinds of different factors, but it can happen pretty quickly. And then there's sort of the other side of this where you might have a system that, again, it's really important to limit these things so that you're not, a bad noisy neighbor. You don't want to exhaust the system of other resources while you use, millions of file descriptors. But you might have a problem where the number of file descriptors being used by an application hits its limit. So the example I'll give is you sort of see peaks and valleys, right? So if you look over time, let's imagine we have a metric that plots FDs, and it's just a counter. Or rather, let's say this is a gauge. I'm just using sort of Prometheus terminology, just borrowing that. But let's say we have a gauge indicating the number of file descriptors used by an application. Typically, if you're talking about like a network application, you'll see file descriptor usage go through peaks and valleys as sort of network utilization goes, up and down. And let's say this is plotted over like the course of 3 days, where we have, peak network traffic, and then we have off-peak network traffic. So you'll see these natural ebbs and flows. And then let's break it down maybe a little bit to a smaller time scale. Let's say like 30, maybe an hour. You'll see sort of more of like a gradual kind of thing, right? Where you're kind of going to see something like that, or it might be increasing. It depends on what side of the curve you're on. But let's say you're sort of going here, but eventually you see the ebbs and flows. A file descriptor leak, it depends on the nature of the leak, but of course it can look something like, normal ebbs and flows, and then all of a sudden it goes kind of straight up. That obviously can happen. So if maybe you make a change to your application, or maybe you didn't make a change, but some latent bug that had the ability to leak file descriptors wasn't triggered until some sort of production event. In production, these things can happen, where that logic fires for maybe the first time, and then that's where the leak takes place. You'll see curves like this. You might also see you might also see a very slow leak, and so like if it's a very slow leak, you might see something like this over time. And so it's really good to have a good understanding of the baseline, because if you can't course, and then of course the other thing that's really important to know is if you're just tracking file descriptors, you might also say, okay, let's have another metric that's showing number of connections, so connections per second. Now, connections, you're talking typically sockets, right? And sockets are file descriptors in Linux. And so if you see this and then you see something like this, it's a pretty good chance that you're leaking file descriptors, because you see the same ebbs and flows, but you sort of, there's a departure between the number of file descriptors that you're using and the connections the active connections that you're seeing at a given time. So this is I bring this up because, again, it's like one of the anecdotes that I can give that I have a good amount of experience with, because the system that I have a lot of experience with tends to have a lot of file descriptor usage, and so something we have to watch on. The example that I'll give here, and again, this will be in the GitHub repository. I made an application literally called fdleak. It's aptly named. Let me show the code here a little bit. It's pretty contrived, but also kind of hilarious. If you go to stream 2, fdleak, it's another Rust application. So what this program does is a few things. You'll see a lot of code related to Prometheus, which I'll get into here shortly. But ignore that for now. If you look at the loop here at the bottom, we call this function called openSocket, and then we count the open file descriptors, and we export that via Prometheus. But openSocket's the important one. So if you look at that, this does something very simple. It just opens a local UDP socket. So I didn't even want to use TCP because I didn't want to depend on like a three-way handshake completing. I just literally wanted to like allocate a file descriptor. I could have opened a file, but again, just wanted to open a socket, something really easy. Now, this is something you should not do unless you know what you're doing. But mem-forget is something you can do in Rust to effectively bypass the automatic drop of that resource. So typically in Rust, when you have there's the ownership concept in Rust. Socket is something that is an owned value in the context of this function, and so implicitly, when you return from this function, the memory allocated for the socket struct, or the UDP socket struct, but the name of that like variable is socket, will be cleaned up automatically because of something called the drop impl in Rust. And it's just a fancy way of saying like real-time garbage collection, effectively, where when that function returns, that type, the actual memory associated with that type, which is typically allocated on the stack, but then also that might point to a heap resource, is literally deallocated right then. So no garbage collection. It's built into the language unless you do some unsafe stuff. It's built in. Mem-forget allows you to effectively bypass that. That's not really the right way of saying that, but in effect, what we're doing here is we're telling we're telling Rust at runtime to forget about this, so that we leave it effectively in memory, and as a result, the socket still exists, the file descriptor still exists. The application just literally forgets about the socket. And so nothing gets deallocated, either memory or file descriptors, and that stays around. And then everything else in this program is really for gathering metrics about this. And so one thing that it does at the top, if you look at the top of the main function, it calls this syscall called setRlimit. This is a way of limiting the number of file descriptors that can be used. I've set it to 1,000, which is exceptionally low. Production values should almost certainly be higher. I just set it to a low value so that we can see saturation pretty early. Everything else is associated with like Prometheus stuff. The getting the number of OpenFDs, another syscall for getting it, for getting the number of for getting the current limit. I think I named I might have named this incorrectly because, yeah, count open FDs, get max FDs, no file. Oh, interesting. Oh, right. Okay, got it. Yeah, so this is subtracting from the limit. Okay, so yeah, so this gets the number of open FDs, this gets the number of maximum FDs, and and then both of those functions are used to export metrics to Prometheus. So I'm going to leave the Prometheus side at that because showing it live will make that a lot more obvious how it works. But the TLDR is this. This application intentionally leaks FDs, so let's figure it out. Let's act like we don't know that that's what's happening and figure out how we might troubleshoot this using the use method. Probably back here, right? Yeah. So if where do I have it? Yeah, FD leak is there. Great. So what I'm going to do first, actually, before I launch this thing, because I think it leaks immediately. I don't think I add like a sleeper or anything like that, which actually I should, but I don't want to do that now. Let me get a few things ready. The first thing that I'm going to do is load Prometheus. Actually, I have Prometheus running on this server, and I'm going to show it here. The program is not running, so Prometheus isn't able to scrape anything. But in the background, what Prometheus is doing is it's scraping the Prometheus endpoint of this application that I built. And it's available on port 9100 when it's running, but it's not running. So right now, Prometheus is probably trying to connect to it, and it's failing. So we run the application. Now Prometheus will be able to connect to it and start scraping its metrics. So what I'm going to do is I'm going to start the application. I'm actually then going to show you the metrics endpoint that Prometheus would be scraping, and that'll be sort of our way of looking at these, like the counters that we saw here for VMstat. It'll be sort of like the equivalent of that. Again, snapshots, like point in time metrics of like how many file descriptors are currently used right now. So let me run this. And that's just going to keep running. But down here, what I'm going to do is I'm going to run a few commands, one of which is curl for the metrics endpoint. So this is literally the metrics that are being exported by the application, and it's literally what Prometheus would be scraping. So process open FDs is 119 when we scraped it, but if we keep running this, you'll see that it keeps increasing. I think I had it do maybe 10 every second, 10 open sockets every second. So it's increasing pretty rapidly. So yeah. If we keep rerunning that, it'll keep increasing, and it will be limited to 1,000. So eventually it'll hit 1,000 and it'll stop. While we're waiting on that to increase, we can also run the lsof command. This is another really helpful one for dealing with files in general, but one that you typically might see for working with file descriptors because it's very helpful in that regard. You could see open files here, but you can also see just sockets here. You'll notice that the node type is actually it shows that it's a UDP socket. You'll see the other ones that we're listening on, and then you see we've hit our file descriptor limit. So now we've reached saturation. Up until then, we have metrics which indicate our utilization percentage, which we can calculate in Prometheus if I rerun this. But now we've hit saturation because now we're seeing errors. So the use method would actually be helpful here. Because if you run it in reverse, you look at errors first. Hopefully, these errors will be surfaced somehow, minimally via some logs. Hopefully, that can then say, oh, like literally, we can't open any more UDP sockets. Like that's the problem. We've run out of file descriptors. So now this is by definition saturation, because it's not by definition saturation. It's errors. We don't know what systems how other systems might react if they encounter this kind of error. And so they may just bail, and in which case maybe there is no work queued up. But either way, if you're looking at like file descriptor usage on the system, we are saturated. And the way that we know that is by looking at metrics. You can see the scrape interval is somewhat large. I should probably shrink that so that this curve is a little bit more obvious. But you see, basically, as soon as we started the application a couple minutes ago, it started climbing pretty rapidly, and then it gets to 100%, which is shown here at the 1 value. So this is the metric process open FDs, looking specifically at the FD leak process itself, and then the denominator is process max FDs, which is set to 1,000. So like if you wanted to look at these independently, you can see that this is now 1,000. If we changed the limit and reran it, it would change with it. And then of course open FDs is just the numerator, and if I can get the query right, stupid autocomplete, you can see that it climbs too. up to, again, 1,000. So the nice thing about being able to do this, like, numerator over denominator, you can just do the division in your Prometheus expression, and then you can put this maybe in like a Grafana dashboard, which is literally like a pie chart, like literally what percentage of our overall file descriptors are in use right now. So just forget about what the limit is, like what is the percentage? How close are we to actually consuming all of the file descriptors? Now, again, I'm still getting accustomed to actually using more of a formal methodology for this stuff, but just to recap, like a way that you could use the use methodology to this is, again, checking for errors first. We would hopefully see these in like a logging system of some kind at a minimum. Saturation then becomes obvious when we consider things like the percentage of max FDs, or the percentage of used FDs over max FDs. It's pretty obvious now that we're saturated in terms of that resource. And if we really wanted to, we can and probably should monitor the raw number, because even if we haven't reached saturation yet, we might be close. And so if you're trying to set up either a percentage pie chart or something a little bit more simple, either way, it's a good idea to have an understanding of what your system's actually using in terms of like just utilization. Because again, if it's not saturated and you don't have errors, but you start to see that sort of like increase I showed, do I still have it here? Yeah, this would be a good example of a performance issue that isn't showing errors because you haven't reached the limit. Right? There's no plateau here. We haven't reached the limit, but it is slowly increasing, and that could be a sort of trailing indicator of an underlying performance problem. Maybe as the number of file descriptors grows, some logic within the application ends up running more slowly, and so over time you have this degradation. Don't have errors yet, don't have saturation yet, but you do have a performance problem, and it will become a more significant problem if you don't get ahead of it. Okay, I suppose that's good there. The only other example I have, I guess this is the third question. This is the final question in the chapter. It says, summarize problems when using average latency as a sole performance metric. Can these problems be solved by including the 99th percentile? So again, going back to the sort of normal distribution, if you're measuring latencies, let's put the file descriptor thing to rest here. If you're measuring latencies, you're performing latency measurements, let's say from a fleet of like 100 servers. It's important to understand when and if like an average measurement is needed, or if you want something a little bit more detailed. So let's get rid of this. Let's get rid of this. So measuring latencies over a set of 100 servers. I'm not going to draw this. What I will do instead is just show the raw data. So the other demo that I prepared is a simpler one, and that is here. It's in the stream2 directory, but I think I have that open? Yes, I do. So latencies .csv. So this is a CSV file. I just had Claude like generate a bunch of like mock data where there are 100 servers, and they're all. Let's just imagine that they're performing latency measurements of some kind. Let's assume it's like time to first byte or something like that. Most of these appear to be somewhat consistent. Like if you sort of eyeball it, you can kind of sort of see that there might be sort of an average of around 50 milliseconds, like a little bit above, a little bit below. But then of course you still see outliers like this, like, oh my gosh, that's like 1.5 seconds. That's kind of crazy. Definitely not all of them, but every once in a while those kind of things stick out. Even visually, you can see that it has like an extra character. So you've got 100 servers here, and they're all performing measurements every 5 seconds. So you've got this like several, 10,000 measurements. And so you're trying to make sense of this. Like for instance, should we try to figure out like, are there specific servers that have these issues? Like, can we characterize the actual where like of the places where the measurement is higher, at what threshold do we care about? Like, do we care about the if we take the average, we'll totally paper over these outliers. If we take like the 80th percentile, we might paper over some of the worst offenders, and it might not actually narrow it. So like you need to play with this a little bit and figure out what you want to look at. So I created this Python script that takes a look at the data and produces the percentile and the average. and 3 percentile. So 50, which percentile of 50 is median, and then percentile of 90 and 99 to give you those percentiles, and it helps you understand where on the bell curve these things sit. So if I run this, let me get this guy out of the way. Oops, I should have been. Oh, am I not in the right directory? Let me copy that real quick. Python. I didn't add a shebang, but I should do that. I'll do that later. Analyze latency. So this again just churns through the CSVs, 100 servers, 12,000 measurements. So the mean is higher than actually I thought. The median, I think I was eyeballing. I actually, yeah, in retrospect, I think I did say mean. I did not mean mean. I meant median because you can't really eyeball the average. What I was eyeballing was the median. So yeah, I was about right, 50 milliseconds. 89 milliseconds is the average, and if you consider that the worst case measurements were like 1.5 seconds, that makes sense. You're now talking about taking into account the weight of all of those measurements, and so it is higher than the median, but it's also significantly below what those outliers look like. And so if you take percentiles, different percentiles of that same measurement, you can see that the P90 is basically no different than the average. And what does this tell you? I think it really tells you that mostly the outliers are relatively few, and they are significantly offset from the mean. And if you want, we can also generate. I don't know if I put this in my walkthrough, but if I do, I think there's. Yes, I did. I created a histogram. Let me actually run that. This is a late edition. I forgot about it. Oh, of course. Hold on one second. So this is the histogram that was just generated. Now, it of course depends on the nature of the data, the data that you're gathering. But if you can plot the P99 using matplotlib in Python, so you can plot the P99 just by taking the P99 measurement and then drawing like a y-axis through that. But what I also did was I adjusted the x-axis to log scale so that it's brought back so that the actual the multimodal nature of the distribution is a little bit more obvious. Otherwise, the outliers, and they really are outliers if you look at it. There's really only a few down here relative to the bulk of the measurements. This is where you start to get a sense of where those outliers actually are and like how many of them there are. So the example that Brendan gives in the book with the disk IOPS, it's a pretty even separation where it's pretty obvious if you look at the two sort of the two areas of the distribution. The average is actually like in the middle because both of them have about roughly the same frequency, and the shape of them is relatively the same. And so the actual average is in the chasm between them. That's not the case here. P90 is pretty close to the median. And the mean is basically right there as well. It's that P99 is so far out because the worst offenders in the top 1% are so significantly distanced from that mean. And so this is something you typically have to play around with. I remember a more recent example when I was playing around with classifying images in the MNIST data set. I had to look at these histograms to understand how to normalize images, because again, you had to sort of make sure that they were that they hit a particular like standard deviation to make them make sense, and like the variance needed to be the same. So yeah, when you're taking measurements like this, having a good firm understanding of statistics, which I don't. I think I did very poorly in college with statistics, so a lot of this was review for me. In the past couple of years, I've had to like kind of catch up on some of these concepts, but it has come in handy a lot. So definitely a tool in the tool belt. Going through my notes, I think that might be it, and I think it's a good time to call it because the stream's been active for just over 2 hours, and the recording is now at that sort of sweet spot, I think probably close to like 1.5. So yeah, I think this would be a good place to stop. Okay, thank you for watching. Thank you for following along. If you're on YouTube, feel free to leave a comment. At any point, I'll be reviewing them. If there's anything you'd like me to cover more explicitly in subsequent streams or videos, definitely feel free to reach out and let me know. I'll be watching those comments. Again, just as a note on GitHub, I was showing it earlier. I have not yet updated it with the book to or with this stream's content. I will do that shortly after. And again, if you're watching the recording, that's already done. So only if you're watching live will that not be the case for you. So for next stream, I will not be streaming next weekend. So a week from today, I will not be streaming, and that would be, I don't have my calendar in front of me. Let me figure that out first before I say anything further. Well, today's the 14th. So yeah, the 21st, I will not be streaming. I believe the 28th, which is the week after that, at the same time, so 1 p.m. U.S. Eastern, is good, but I will have to probably keep an eye on that. So stay tuned to my socials. If you aren't already, oswalt.dev/links. Check those out. There's a link in the description to all of that. If you look there, I will try to do my best as early as possible to let you know if there are any changes to that. But at the moment, my plan is to cover the next portion of the book 2 weeks from today, and that again is the 28th, March 28th at 1 p.m. U.S. Eastern Time. Now, I looked ahead a little bit, and Chapter 3 is actually somewhat small relative to Chapter 2. It's a little smaller. So if we're able to do all of Chapter 2 today, which I might have probably accomplished only by skipping a certain section or two, but still, if we were able to do that today, then I think Chapter 3 is definitely doable. So my current plan is, at that time, so the 28th at 1 p.m. U.S. Eastern, cover Chapter 3 of the book, Systems Performance by Brendan Gregg. If that changes, I'll let you know, but I think that's a pretty good target. So yeah, stay tuned for any changes, but that's the plan that I have now, and I will do my best to let you know if any of that changes. So thanks again for watching, and I will see you next time.